All right, so up at this point, when we were looking at the rate constant, when we were looking at K, um, it was going to be the same for a given reaction because even when we were changing the concentration, we were assuming the temperature was going to be constant. And the rate constant is going to be temperature dependent. So if we look at the graph here, generally what we're going to see is something similar to this, where as we get to higher and higher temperatures, we're going to see that the rate constant, meaning the speed of that reaction, is going to increase. So if you look at the picture here, kind of similar to a glow stick, this is going to be a reaction that's going to give off that light. And the more of the reaction that we're having, the more light that's going to be produced. So with the reaction in water versus the reaction in the ice, with the higher temperature, we're going to have that higher rate constant. So we're going to see the speed of that reaction is going to increase. So for the most part, we'll see the temperature of a reaction and the rate of the reaction are going to be directly related in the sense that as the temperature goes up, the rate's going to go up as well. And when we're looking at a reaction, what's actually going to be happening is the molecules themselves are going to be coming together, and we're going to have a collision, and that's going to be where the bonds are broken, as well as the new bonds being formed. So if we look at the reaction here, we're going to have kind of two components of this collision that we're going to need. One's going to be related to the orientation, so we're going to need the correct part of these molecules to be interacting. So in the case of this one, we've got just a green atom, and then the molecule has got green, blue, and red. And in order for this reaction to occur, we're going to need those two green pieces to come together, so we can form the diatomic green molecule, and then just the blue and red one. But if we switch this molecule around, so we've got the red and the green coming together, we're not going to have the correct orientation, so we just may not have a reaction take place. Or if we do have a reaction take place, it's going to be a different reaction in that case. And then the second piece is going to be related to the energy. So we're going to need a sufficient amount of energy in order to break these bonds. Otherwise, the reaction is not going to take place, even if we've got these interacting correctly. So when we're looking at a chemical reaction, we need the correct orientation for those molecules, as well as a sufficient amount of energy. And then with this, that's kind of with the exception of a decomposition reaction. So if we think about taking one substance and just having it break down into multiple pieces, take that one substance and have it break down to multiple pieces. In that case, we don't have a collision occurring. We're just going to have some sort of energy gain that's just going to make that molecule unstable. So typically, if we heat something up enough, we can have it decompose. In some cases, like with hydrogen peroxide, sunlight could break the bond and form a new substance, so it could break it down into water and oxygen. But with the mixing of chemicals where we've got multiple reactants, we're going to see a collision like this. And then with the sufficient energy piece, what you can kind of think of it as is getting a ball to roll over a hill. It's not going to naturally just automatically go from, in this case, the left to the right, because we've got kind of an energy barrier here. We're going to see the same thing with these reactions. Even though we've got the reactants mixed together, if we don't have them overcome this energy barrier, we're not going to have a reaction take place. And we're going to just call this energy barrier the activation energy. So this is going to be the minimum amount of energy needed in order to get the reaction started, or as the term activation energy would suggest, to activate that reaction. But just like if we're playing golf and we putt this ball, if we can get it to the top of this hill, it'll just roll down the other side. Same thing when we're looking at a chemical reaction. If we think of this as our activation energy, if we can get the reactants to an energy where they're going to be above that energy barrier, they'll have enough to get converted into the reactants on the other side there. And what we can do with this process, or with this sort of concept of the energy of a reaction, is plot it on what's known as a coordinate diagram, or a reaction coordinate. And essentially what it's showing on the left is our pure reactants. On the right are pure products. And then in the middle here, it's showing how the energy of the substances are changing as we go from reactant to product, because what we're going to see with a lot of these reactions is it's not going to be just a single step where we go from reactant to product just like that. We're going to have something like we see here, where it's going to be a multi-step process. So even though this is just looking at converting the carbon and the nitrogen, essentially just switching them within one molecule, but it's still going to be a multi-part process where we kind of see the bond angle change. Then we're going to have the complex form where we don't even have these really truly bonded anymore. And then it switches around again, and we've got the bond changing one more time, the bond angle changing one more time, I should say. So with the potential energy here, we're just showing that how it's going to change with these different sort of steps within this reaction. And then with it at the top here, the activation energy, that barrier we need to get over, what we're going to call the substance we have is the activated complex, and it's also going to be known as the transition state. So it's the midpoint of the reaction. Essentially, it's the transition from reactants into products, and it's going to be the energy barrier we need to overcome. And then looking at these coordinate diagrams, there's a couple of different energies we can focus on. So the difference between the reactants and the products is just going to be the change in energy overall. And then with the activation energy, just know it's going to be the difference from where we start to where we need to get to the top. It's not going to be the entire thing. So if we, for instance, let's just say we have 0 at the bottom here, 40 at the start, and then 100 at the top. We need to get the reactants to 100 kilojoules of energy. But since they're already starting at 40, the activation energy would just be 60 kilojoules in that case. And then we could also, in some cases, read these backwards, where the reverse reaction would be then going from the right-hand side to the left. And in that case, the activation energy would be a little bit taller for this one. A little bit larger, I should say. And then with the activation energy, the reason we're going to see that the temperature is typically going to be directly related to the rate, in the sense that as we increase temperature, we increase the rate of the reaction. The reason for that is because as we increase the temperature, we're going to be increasing the energy of these molecules. So this is what's known as the Maxwell-Boltzmann distribution, but it's essentially just showing us how the molecules in a sample would be distributed in terms of their kinetic energy. Because when we're looking at temperature, it's a measure of average kinetic energy, but not all of those molecules are going to have the same. We're going to have a distribution like we see here. But at higher temperatures, so with the red one, we see the curve starting to flatten out a little, because what's happening now is we're pushing more of these molecules to the higher end. So if this dotted line is our activation energy, we can see at a higher temperature, we're going to then have we're going to have more molecules that have an energy that exceeds that activation energy, exceeds that energy barrier. And then since we have more of the molecules with enough energy to react, that's why we see the reactions start to occur faster, because we essentially just have more of it actually happening now. And then in terms of actually calculating how many of those molecules are going to have a sufficient amount of energy, we've just got this equation here where EA on top is the activation energy, R is the gas constant, and then T is the temperature in Kelvin. And a couple things to point out with this is the R value. So remember, we can have a whole bunch of different units on the R constant. But for this one, we're going to want to use the 8.314 joules per mole Kelvin, because with it, the activation energy is going to be in joules, or it could be in kilojoules, which in that case, we'd have to just move this over a couple spots, the decimal there. But it's going to be in joules or kilojoules per mole. And then the temperature is going to be in Kelvin, so that'll allow all of these units to cancel. And that's why we'll just be left with a fraction or a decimal, really. But with this one, if we note as the activation energy increases, that's going to make this negative exponent larger, which is just going to make the fraction smaller. So as the activation energy increases, we're essentially just moving this line further to the right. So we'll have less of the molecules having a sufficient amount of energy. And then with the temperature, as the temperature increases, we're going to have a larger denominator, which is going to make this number smaller overall. And since it's negative, that'll actually make the fraction larger. So that's why as we increase the temperature, now we'll have more of the molecules having sufficient energy as well. And then we can kind of take the relationship between the rate constant and the activation energy, and it's what's known as the Arrhenius equation. So if you're familiar with acids and bases, we also have Arrhenius acids and bases named after the same guy. But essentially, this just allows us to calculate how the rate constant is going to change with temperature. And then A is just going to be a frequency factor. So the likelihood that the collisions of those molecules are going to occur with the correct orientation. So meaning we'll have the correct pieces of those molecules actually lining up. But again, activation energy EA, gas constant, and temperature in Kelvin. And then the A again is just at that frequency factor. So we can calculate what the rate constant is going to be if we know what the activation energy is and the temperature. And if we modify that equation a little bit, we can get the natural logarithm, so ln of both sides. And since we had this raised to the power of e, basically just becomes that stuff by itself, natural log of a, natural log of k, and we can see just the graph here. And then with this graph, the inverse temperature, just note that that means the left-hand side is actually going to be our higher temperatures. So that's why we can see the rate constant is increasing. It's higher up on that side because this is going to be where we have the higher temperatures, whereas the right inverse T will have a smaller number on the bottom, making that number overall larger. So we'll have the lower temperatures on this side. And then with these reactions, kinetics, so far we've been mostly focused on the rate of the reaction, how fast does it proceed. But kinetics is also going to be interested in how a reaction occurs. And sometimes it's not just going to be a single step. Sometimes we're going to have multiple steps there. And when we do have those different steps, we're going to refer to them as elementary reactions or elementary processes. Because when we look at a chemical equation, a lot of the times we're going to think just reactants, two products, because that's what we start with, that's what we finish with. But a lot of the times we're going to see there's going to be, kind of as the coordinate diagram indicated, there's going to be multiple steps where we're kind of having those molecules sort of transition from the reactant to the final product. And what we have here is just a mechanism. And we have a couple different things we're asked to do for this two-step mechanism. So two-step just because we got two different reactions kind of pieced together. First, describe the molecularity of each elementary reaction in this mechanism. So what that's referring to is how many different molecules do we have reacting in that particular step. So for the first one here, this would be known as unimolecular. Just because we've only got one molecule to start, we just have that single ozone, so O3 is just ozone. We just have that basically decomposing to diatomic oxygen and then the single oxygen atom. Whereas the second one would be considered bimolecular because now we're having two molecules come together. And then if we had a third one, which is less common, because if you think about it, we're going to need three molecules to hit each other at the same exact time with the correct orientation and the correct, or with sufficient energy. And that's going to be pretty rare. So we're going to typically just have unimolecular, bimolecular. But if we had three come together, sometimes it's referred to as termolecular. Sometimes it's also referred to as trimolecular. But with these two, we're going to have uni and bi just because we've got one ozone in the first one, and then an ozone with an oxygen atom in the second one. All right, and then with the part B here, write the equation for the overall reaction. So this is going to be similar to what we do with Hess's law, where we can kind of piece together multiple reactions, add up everything on the left, add up everything on the right, from the multiple reactions, and then anything that occurs on both sides kind of gets canceled out. So we can do the same thing here, actually. And if we look at it on the left, one oxygen atom, on the right, one oxygen atom. So those are going to cancel. And now on the left, we've got two ozones. So we'll have 2O3. And then on the right, we've now got three oxygen molecules. So we'll have three, 3O2 there. And again, you could write everything down on the left, write down everything on the right, and then see these two cancel. Or in some cases, you can kind of just piece it together by looking at it. This one's not too bad, just because we've only got two of the reactions. But sometimes we'll have three, or sometimes we'll even have just more stuff going on here, which can make it a little trickier. But then with the final piece, identify the intermediates. That would just be the things that are going to get canceled out on both sides. So this oxygen atom would be considered an intermediate because it gets produced in the first step, but then it gets used up in the second one. Whereas the ozone, those are both just reactants because that's what we start with. And then the O2 are both just products because we're finishing with both of those things. Or I guess one thing. We've just got it split up into two steps here. And then with this, we'll also be able to use the mechanism in order to determine what the rate law of a particular reaction is going to be. In this case, we don't have enough information about these two steps. But if we look at the one here, we're going to be able to figure out this rate law, assuming it does occur in just a single step. Because what we're going to have is a rate like this. We'll have, in this case, rate. And then since we've only got one step, this is going to be what's known as the rate determining step. So we'll have K, whatever that's going to be. And with the rate determining step, we can essentially just look at the coefficients and use those as the exponents. So if this is the only step of this reaction, what we're going to see, since we've got a coefficient of 1 for both of these reactants, is that the overall reaction is going to be second order, because each of these reactants are going to be first order. But what we'll see is in cases where we've got multiple steps, we've got to actually identify what's going to be the rate determining step. And with this reaction in particular, based on experimental evidence, what they've determined is that the rate of this one is actually going to be 1/2 for bromine, which indicates that this is actually going to be a multi-step process, because this rate law doesn't just match up with this equation right here. So it's because we've got a difference with the exponent and the coefficient. That means we're going to have multiple steps of that reaction. And if we look at the decomposition of nitrous oxide, so N2O, we can write the overall reaction first. So we can see the oxygen going to cancel, but we got two N2s, or two N2Os, I should say, on the left. And then we've got 2N2 plus just that single diatomic oxygen. And then with this one, we also want to get the rate law. So like I said, we're going to have a rate determining step, and that's going to be the slowest step we have, because with this is going to be kind of the one that holds up the reaction, essentially. So when we're thinking about the rate, this one's going to happen extremely quickly. But if we look at the reaction here, this one requires oxygen, that oxygen atom. That oxygen atom gets produced in this step. So even if this reaction at the bottom goes extremely, extremely quickly, it can only go as fast as the oxygen's produced in this first step. So the rate determining step is going to be the slow one. And this is going to be how we determine the rate law of this reaction. So we can look at the rate determining step. We can look at that slow step, and we can write just a rate law for that step. And that'll explain the reaction overall. So in this case, when we look at the slow step, we've got rate is equal to K, and then we've got N2O. But since we've only got one N2O in that reactant, we're just going to keep it single or first order. We're just going to have that one exponent there. So the rate law would just be the rate is equal to the rate constant times the concentration of N2O. Because even though we've got two of them in this reaction here, if you think about it, we kind of got them split up where the first one needs to be used so we get that oxygen. And then that oxygen can react with the N2O. But as we increase the concentration, it's really only going to still matter based on this first reaction. So since we're only increasing that one by one factor, basically, we're just seeing the single exponent there as well. And a factor I shouldn't have said just because that refers to 10. But if we think about doubling the concentration, we'll just see this first one get doubled. So that's going to be, or the rate of that first one get doubled. So that's why we're just seeing the first order coefficient there, or exponent rather, excuse me. And if we look at the setup here, sometimes they use sort of toll booths to explain the rate determining step. Because with it, if we think about Plaza A or toll booth A being the rate determining step in this one, so it's going to be the slow one, we can have this second toll booth be as fast as it wants to be. But if we're holding everybody up here, they're never really going to make it here. It's going to still take them a while. So the rate at which they make it through both of these toll booths is going to be dependent on this first plaza. So it's similar to our first reaction being the rate determining step. And then with the second one, now we're seeing kind of the same thing. They can make it through the first one, no problem, but now they're getting hung up at the second one. So now this would be our rate determining step. This is going to be what we base our rate law off of. In some cases, though, we'll see the rate determining step may have intermediates as one of the reactants. And in that case, we're going to have to kind of adjust our process a little bit. But if we look at the reaction here, NO2 plus carbon monoxide gives us NO and carbon dioxide. So we're essentially just having the oxygen switch from NO2 to carbon monoxide. We see the rate law for this reaction is found experimentally to be rate is equal to the rate constant times the concentration of NO2 squared. So this is going to be a second order reaction because as we double NO2, we'll see the rate's going to quadruple. And what this tells us, what these two pieces of information combined tell us, is that the carbon monoxide is of course going to be completely necessary for the reaction. If we just remove carbon monoxide completely, we're eliminating one of the reactants. We can't have the reaction occur. But it's also telling us that the carbon monoxide concentration isn't going to affect the reaction at all, or the rate of reaction at all, I should say. So that tells us we're going to have this reaction occur in at least two steps. So because this rate law doesn't match up with the overall equation here in terms of the coefficients and the exponents, that tells us that this is going to be a multi-step process. So when we look at the mechanism here, what we're going to see is that two of those NO2 molecules are actually going to react together, and one of them is going to take one of the oxygen, so we'll wind up with NO3 and NO. And then that NO3 is going to react with the carbon monoxide to essentially just lose the oxygen it gained to get back to NO2 and CO2. So when we look at the overall reaction, this NO2 is going to cancel one of these. So our overall reaction, same with the NO3. So our overall reaction is really just NO2 plus carbon monoxide goes to NO and carbon dioxide. But because this is the rate determining step, that's why we're still going to see the rate law is going to have the concentration of NO2 squared, because we have two of these in the rate determining step. So as we increase the concentration, it's going to, as we double it, for instance, it's going to have a fourfold effect. So with it, when we're looking at the mechanism, if we know the slow and fast steps, we can write the rate law for the overall equation based on that slowest step. And as long as that slowest step just has reactant molecules that are actually reactants in the overall equation, we can pretty much just stop there. So that's why we can just write rate is equal to K, a concentration of NO2 squared. But if this had been our rate determining step, so if the step 2 was the slow one, then we'd have to kind of go back and look at our first reaction a little bit. And we'll see an example of that as well. No, and then with this one, so 2NO plus the diatomic bromine gives us 2 molecules of NOBr. And we see the rate law shown below, or shown on the screen, I should say. So rate constant times the concentration of NO squared times the concentration of bromine. And that actually matches up with the coefficients of this equation. But this would be, if you look termolecular or trimolecular, this would be suggesting that we have all 3 of those molecules come together at the same time with the correct orientation, which is going to be pretty rare. So just the fact that we've got 3 molecules in the reactant side suggests that this is going to be a multi-step process. And when we look at the mechanism, we can see that that's going to be the case. So we'll take one of those nitrous oxide molecules, excuse me, and react it with the bromine to give NOBr2. And then we'll have the second NO react with that molecule just to essentially take one of the bromines. But this bottom one is going to be the rate determining step now. So if we write the equation there, oops. Okay. So rate is equal to K but you'll note that the first step up there at the top is actually a reversible reaction. So we've actually got an equilibrium with the both sides of that reaction. And then with step 2, where we actually wrote the rate law, because that's our rate determining step, one of those substances, the NOBr2, actually isn't a reactant of this one. So we can't just directly change the concentration of NOBr2. Like we can't just add that to our reaction. So what we're going to see is we'll have to adjust this one a little bit. We'll have to think about how we can kind of substitute something in for the concentration of that intermediate. And what we're going to do is think about the first step where this is actually being created, where we've got that reversible reaction. And what we're going to be able to do is think about the rate of the forward reaction is going to be equal to the rate of the reverse reaction. So we're going to be at equilibrium. So we'll be taking the same amount of those reactants, converting them to products, as we will be taking those products, converting them back to the reactant. So what we can do is write that first rate law. The rate constant times the concentration of those reactants, because we were combining them to form this. So K1 is just referring to the rate of the forward, K-1 referring to the rate of the reverse. And if we solve for the concentration of that intermediate, then essentially just divide by K-1 from both sides, we get the equation at the bottom here. So then what we can do is go to our rate determining step, go to that slow step, and instead of expressing it in terms of the concentration of this intermediate, we can plug this in its place, and that's where we're going to see the square of the concentration of NO, because we already had one of those in the equation, and then we'll get the Br2 with it as well. Yeah. So again, we substituted in K1 over K negative 1, and then NO and Br2. And then when we really just combine it, because we can have these squared now because they're the same term, and we can just simplify all of these rate constants just into the overall rate constant for K. So these 2's and 1's just refer to the rate constant for those individual steps. All right. And then with these reactions, what we can do is, in some cases, sort of help them along, speed the reactions up. And the way we're going to be doing that is by using a catalyst. And the catalyst is essentially going to offer the reaction sort of a shortcut. It changes the mechanism by which the reaction occurs. And what it does is it lowers the activation energy. So it takes a more favorable sort of path from the reactants to the product. So if you look at the picture here, the red one is just the uncatalyzed reaction. So we see that bump in the middle as the activation energy. But then when we use a catalyst, now these transition states, these activated complexes are going to be different. So we're taking a different path. And since it doesn't go quite as high, it's not going to need quite as much energy in order to get from the reactants to converting them to the products here. But you'll notice with the catalyst, it doesn't change anything about the reactants or the products themselves. So that's why we're still starting and stopping the reaction at the same points with the same substances. It's just sort of the path we take to get there is going to be different. And one way this occurs is essentially by allowing helping get the molecules, those reactants, in the correct position in order to actually react. So in some cases, it can kind of hold the reactions in place so that the other reactant can then come by and react with it. And then with these catalysts, when we have them occur in biological systems, they're just going to be known as enzymes. So you can see here the substrate fits into the enzyme, kind of just like a key, and then it just allows that process to occur.